Hello, this is Mike at Gamefromscratch. Welcome back to our ongoing MonoGame tutorial series. Today we're going to look at starting to program in 3D using MonoGame. Now, if you've worked in any other 3D game engine in the past, you're going to probably think that the level of code that we're about to do here is a little excessive. The reality is MonoGame works, or XNA in general, works at a fairly low level. There are high-level constructs like we're going to see with the 3D model support, but a lot of times you're working almost at an OpenGL or DirectX level where you're creating your camera, you're creating your primitives, you're doing all this stuff by hand. Now there's all kinds of community projects and such available that build on top of XNA for you. So if you don't feel like reinventing the wheel like we're sort of about to, don't worry, you don't have to. Now, as I said earlier, there's no camera class built into XNA. However, there are full matrix classes in there and a lot of convenience functions, as we're about to see. Now, theoretically, this chapter, this portion we're about to cover, is fairly math intensive. However, the reality is you have to more or less understand when to use something, not necessarily how to use it. Think of an analogy of if I ask you to calculate the sine of something, that's not particularly an easy task to do. You'd have to learn how to do sine curve calculations, or you can go to your calculator, punch in the number, and hit the sine button. Essentially, the math behind XNA is the same way. They're providing that sine button for you. They're providing pre-built vector 3 classes, matrix classes, and all the stuff you need. So you've got to roll your own camera, yes, but the reality is a lot of the functionality is there for you, so it's not as scary as it sounds. Now we're also going to have to roll our own primitive. Amazingly enough, out of the box there are no primitives in XNA or MonoGame. So there's no cubes, there's no teapots, there's no polygons even. Everything is done basically from scratch. And generally what you would do is build your own libraries and go from there up. Now that's not completely true. There's also a model class used for importing 3D models into the content pipeline. And that we will see as well. And that does make the burden of taking complex objects into your scene and makes it a lot simpler. There's also, if you go to Gamefromscratch.com and see the analog, the text version of this post, I've linked to a couple of important sources. One is a library that provides primitive support for you. So if you want to add things like basic spheres, cubes, teapots, etc., there's a link there. It's a single code file you add to your project, and then you've got these primitives. So it's not really hard to acquire a more high level of support, but what we're about to do today is fairly low level stuff. The other thing that's on that site, though there's two more things on the Gamefromscratch webpage that aren't here, obviously, because I can't do it. One is the 3D model that we're going to import. I also did a video showing exactly how I created and exported that model from Blender. So if you want to create it yourself, look in the comments below. I'll give a link to that video that shows how I created the 3D model we're going to use. There's also a link to 2 math books that I recommend. So if you are struggling with the math behind gaming, I linked off to 2 books on Gamefromscratch.com that are considered very popular, very useful for learning 3D game-oriented math. So if you want to learn the math a little bit better, go there. There's also a link to Khan Academy. Khan Academy is a free university for teaching these math-type subjects. Excellent source, and it goes way beyond what I'm capable of doing. Like in all honesty, even just teaching about matrix multiplication would take me a couple of hours in tutorial. I can't cover that kind of stuff, so I'm going to have to assume that you'll either know it already or you can figure it out. So anyways, that's that. Now let's jump on in and get started. Here's my project. Let me just go ahead and set one up. So, new XNA game project. Let's load up our class right here. Zoom in a bit so you can see what I'm doing. And give me a sec. I'm just going to prune out all the stuff we don't need. Alright, that trimmed out the comments. Now I'm going to show you part of what I'm about to take out, because this is actually kind of important. Up until now, we've been dealing with 2D sprites and something called a sprite batch. In this case, we are not using the sprite batch anymore. I actually, on my Gamefromscratch.com example, forgot to actually remove this, but we don't need it. Just take that out. Sprite batches is sort of a virtualized 2D presentation. We're working completely in 3D. We do not need it. We're going to use something kind of equivalent called a basic effect, and it's going to perform pretty much the same functionality. Plus we're also going to have to go ahead and, like I said, create that camera. Now in order to understand cameras, I'm going to have to give you a very, very, very small math lesson. Very, very simple. But basically, the shader behind the scenes, the graphical routines responsible for drawing your primitive shapes or your triangles, etc., onto your screen as pixels require 3 different matrix calculations. And the nice thing about matrix calculations is they're additive. You could multiply them together. So basically, multiplying the 3 together gives you the results of working with all 3 independently. So it creates basically our camera calculation. And it's of 3 parts. And we're going to need, let me go ahead and add them as I'm describing them. We're going to need 2 vectors, first off. Vectors are just x, y, and z coordinates in 3D space. We're going to need one for where our camera is pointing. We're going to need one for where our camera is. And then now we need those matrices I was talking about. So we need a matrix for projection. We need a matrix for view. And we need a matrix for world, like so. And a bit of an explanation of what each one of these is. Very, 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 very high level, probably poor explanation, but an easy one to understand. Is basically your world matrix is responsible for positioning your entity into the world. This is your position and rotation in 3-dimensional space. It's calculated from this guy. Otherwise, everyone would just be sitting at the origin and it wouldn't be that interesting. So the world matrix projects your object into the world. So if something exists somewhere in the world, this is the matrix responsible for doing that calculation. Now, these two, think about them working together as part of a camera. And your view matrix can essentially be thought of as the camera's position. Your actual physical camera is somewhere in the world, and the view matrix figures that part out for you. It's the location and orientation of your virtual camera. And then your so which one did I talk about there? That's your view matrix. Well, your projection matrix is sort of responsible for taking 3D and turning it into 2D. Now, to stay with the camera analog, analogy, if the view camera is the camera itself, the projection matrix is the camera's lens. This is what turns and figures out what a camera can see, how it can see its field of view, how far it can see, and is used in calculating how 3D gets mapped into 2D. So think of it that way. Your world matrix is your position in space, your view matrix is your camera's position in space, and your projection matrix is the lens of your camera. So those 3 things go together to turn something from a 3D object to a 2D pixel you could see on your screen. And that's a very, very simple way of thinking about it. Probably wrong, but it's easy to understand. All right, so let's go on. We're also, as I said earlier, we're going to need a basic effect. This is the equivalent, this is basically a wrapper around the HLSL shader that's used behind the scenes. I'll go into that in a few minutes, but let's just go ahead and create it for now. So this is what we would use a sprite batch for in the past, but it's for 3D instead. And it's kind of the shader that tells XNA how to draw your 3D objects. Finally, we're going to need geometric info. This is what we're going to draw. Basically, we're going to create a triangle from scratch. And a triangle is 3 vertex position color values. Now, that variable name is very self-evident. It's a piece of data that holds vertex, so x, y, and z coordinate. Sorry, wait. Yeah, vertex, sorry, it holds a vertex position, so the x, y, and z coordinates of that vertices, as well as color, RGBA information. There's other ones like this. Let's see if I can bring them up without. So, see, you got your vertex position color if you want a vertex with color data. You've got vertex position color texture if you want to have texture mapping, and vertex position normal texture for texture with. Actually, I thought textures needed normal. Anyways, you have these different base vertex classes that you can use. In this case, we just want a colored vertices in space. So if we wanted to texture map our shape after the fact, this one won't work because it doesn't contain normal's position. Normal tells 3D which direction your shape is facing. So we're using a vertex position color array triangle vertices. So that's the array of data going to hold up our vertices. Now you use a vertex buffer to actually draw them to the graphics card. And later on, float orbit. This is for, we're going to actually make our camera functional. It's going to be able to pan, zoom, and rotate. This is going to be used for the rotate part. So I'll just put that in for now. Oh, actually, no, sorry, that's a bool. Are we rotating or not? We're going to rotate at a fixed amount if we are rotating. All right, so that is that. That is fine. And initialize is where all of our magic works. And the very first thing we're going to do in initialize is set up our camera. So our camera is basically a combination of that vector 3 for position, vector 3 for target, and then those three matrices, the view, projection, and world matrices. Now, one thing that's really important, and I'm not doing it here, but you in the real world, if you're doing this for your game, wrap this all in a class. Very, very simple. You can then easily map all this together. And the truth of the matter is, most of these values don't change. Like the view changes for sure, the position changes for sure. Your projection matrix of your camera generally won't change all that much. So it is definitely one of those classes that, or one of those things that is a very good candidate to be wrapped into a class with a couple of helper functions around it. Again, I'm a little shocked that this isn't out of the box. I would have thought this was common enough that they would have created a basic camera class. All right, so cam target. These numbers are pretty arbitrary. You can use whatever coordinates you want, just be consistent about them. So we're using 0, 0, and 0. So basically our camera is pointing at the origin. Our position is going to be vector 3, 0, 0, minus 100 f. So basically we're dead centered but pulled back virtually out of our monitor, looking at that point. So we're just moving our camera along the z-axis so you can actually see what's pointed at it, what it's pointing at. So now we want to create our matrices, or matrices. So projection matrix. This one is, as I said, this is the camera lens you can think of. We use matrix dot. And like I said, there's a whole bunch of helper functions built in there. And the first one is we're going to use is create perspective field of view. Now, this create perspective, there's another option for cameras. There's two types of cameras in the world. This one we're going to use perspective because we're working in 3D. There's another one called orthographic. Now, the only real big difference between orthographic and perspective is as things get virtually farther away. So as their z coordinate changes and they move further away from you. With orthographic, they stay the same size. Whereas the perspective camera, the way your eye works, as things get farther away, they appear to be smaller. Functionally, obviously, you know, if you walk 100 feet away from your car is going to be the exact same size it was up close, but it's going to appear to be smaller as you get further away. And in the same level, if you look at a building, the front of the building is going to look of a certain size, but the back of the building is going to look smaller because, again, it's further away from you. That is the perspective phenomenon, and the creating a perspective projection basically recreates that. So, nutshell version: working in 3D, create perspective. Working in 2D, where you're with sprites, etc., create orthographic. And so that's that perspective, and we're going to use a field of view. Field of view is think about it as the angle you can see in front of you, or your these things all go together to create something called a view frustum, which is both the angle you can see at and the distance you can see out to. Think of it as a triangle representing, or a pyramid representing what's visible to you in the world. Well, field of view is, again, the angle you can see left and right. Now, in reality, the human being has a field of view of about 170 degrees, 180 degrees, which means if you hold your arm straight out beside you and strain without moving your head, you can basically see both arms. So that's your view radius is about 180 degrees. Now the reality is, though, about, I'd say, half of that is peripheral vision. And in a monitor situation, or when you're recreating it, you don't represent peripheral vision. You want to have your active vision only. And the value you use for field of view kind of comes down to how you're watching it. And what that generally means, if you're a PC gamer and you switch and you play a console game on the PC that's got its field of view locked, a lot of times it's very screwy for you. And the reason behind this is console games are written with a much narrower field of view. They're along the lines of say 65 degrees, whereas on the PC your value is normally about 90, and that's because of the distance that you sit generally from your monitor and the size of your monitor in each of these environments. So when you're sitting on a couch looking at a big screen TV, to get and mimic the real world better, you generally have a narrower field of view, whereas if you're up close to your PC sitting at a desk, you have a much wider one, like I said, 90 to 100 degrees. I don't know the answer to which one to use. In this example, I'm actually using 45 just because. But you can enter whatever value works for you, or if you're working on a PC game, I would highly recommend making this actually a settable value. Now, one thing to be aware of, though, is if you make field of view configurable, it changes what is visible. So a wider field of view shows more data on screen. That means if you're creating, say, a first-person shooter, and I have mine set to 90, and you have yours set to 65, I have like 30 degrees more visibility to you. I can see things that you can't. I can see you before you can see me. And, you know, sometimes people are cool with that. Sometimes it's straight out cheating. So just be aware that changing the field of view does in fact impact what is visible. All right, so lesson behind, we're gonna create a matrix 4 with the create projection field of view. So that very first value we need is a field of view. However, it is specified in radians, not degrees. I don't know why, it just is. Thankfully, converting between radians and degrees is quite simple. It is quite simple anyways, but there's actually a math helper class available to make life easier for you. So it's math helper .to radians, and like I said, we're going to use 45 degrees. Next up, we need the aspect ratio. This is your ratio of width to height. It's literally the width of your display divided by the height of your display. This tells basically the monitor. It tells it how wide or high your display is ultimately going to be, and that is available in a class called graphics device display mode aspect ratio, like so. And then finally, we've got our near and far plane. Near plane we will use 1, far plane we will use 1000. Why? I picked those numbers out of thin air. Truth of the matter is those are just the values that are often used in examples, so I'm staying with convention. But this is, remember I told you, think of this whole thing going together to calculate this pyramid of what's visible. This is how close to start seeing. You could set it to 0, but that doesn't really make sense. Basically, this would be, say, the tip of your nose is where you can start seeing things, and then 1000 is where the rendering stops. So if you have something and its coordinate is 1001 z, or along whatever axis you happen to be looking, if it's at 1001, it will not show up at all in this camera. So that's what those two values are, the near plane and the far plane. So the field of view, near plane, far plane, and the aspect ratio all to go together to calculate this virtual pyramid of visibility. Okay, so that is your projection matrix. That's by far the hardest one to make. So now we will go on to the view matrix. And again, this is basically your camera's virtual position in the world. So matrix.create, again, there's a nice function to, as I said earlier, you need to know the math, but you don't need to know the math. Figuring out how to create a look at matrix, how to create a perspective field of view matrix, etc. There's a lot of math involved in that. Calling a function to just go ahead and do this, there's not a lot of math involved. So you need to know some math, but you don't really need to know the math behind it to use this stuff. You just need to know that it's available. So we got our camera position, our target, and cam target, and then finally our up vector. And this is actually defined in vector3.up. This is telling the world what our orientation is in case you're going to override it. Now, this vector3.up is the equivalent of this, which is saying up and down in your world is along the y-axis. So unless you're going away from the norm, just go ahead and use vector3 up and you're good to go. Now this is something to be aware of later on. Different programs, for example Blender, and different game engines, for example XNA or MonoGame, use different axes for where up and down is. For example, in Blender, up and down is the z-axis. In XNA, up and down is the y-axis. So then you run into this situation of your models are exported basically rotated by 90 degrees. It's easy to fix. First off, you can just rotate your model 90 degrees. Or a lot of times on export, you can say, use these coordinates, etc. But it is one of those things to be aware of. If you do bring a model in and it's rotated 90 degrees on you, it's probably because it was created in a system that has a different up than your game engine. Okay, so that is your view matrix done. And your world matrix is matrix.create world. See, nice, all these nice helper functions make life easy for you. And I don't know why I did this in my other example, but I'll go ahead and do it again. That's just basically saying 0, 0, 0 in a very gross way, so I'm not sure why I did it that way. And then vector 3 dot forward. That's an angle orientation vector, and then once again, up. So your world matrix is basically at 0, because we're not moving anything as of yet. We're not really using it, if we're honest. But let's see. Next up, we need our basic effect. This, as I said earlier, is the equivalent of a sprite batch, but in the 3D world. And what I'm saying that is, there is actually an HLSL, or high-level shader language. I don't know, Microsoft's DirectX version of GLSL, the programmable shader programming language. Well, behind the scenes, this basic effect is what's figuring out how to project things from 3D to 2D, and all the special effects, etc. to do on it. There's multiple passes, there's lots of neat things you can do in shader programming, there's lots of power there, but way beyond the scope of what we're talking about here. Now, I might do a tutorial about shaders specifically in MonoGame in the future, in which case I'll get into this in a little bit more detail. But so you have a bit more understanding of how basic effect works. The nice thing is Microsoft actually made the source code available for us. Give me a second and I will bring it up. Ta-da! I could give you the link for this if you can't see it at the top, but it's also linked from Gamefromscratch.com, the text post, which I will make available at the bottom of this in the comments. But it's the stock effect sample actually contains the source code for base effect. And let's just go over and open that guy up. I've already got it downloaded. There we go. Let's just bring this guy over here. And this is the contents of that download. This little, what is that, very, very small, 0.07 megabytes file. And it's a Visual Studio, pair of Visual Studio solution. And what we want is stock effects. And we'll go into HLSL. And you'll see right here, this is the shader code for that. Now again, we're going way, way beyond what we want to cover by actually what this is doing. But like I said, this is basically responsible for transforming all of the vertices in your scene. And this is sort of the program that tells it how to do things. Like here, this is multiplying the out value of diffuse, multiply equals the in value of color, that kind of stuff. This is a textured shader. This is to do the texture mapping. This is to do texture mapping without fog, texture and vertex color mapping, etc. These are little programs basically that are transforming all of the vertices or all of the texels of your screen and making them visible. So it's the basically scripting language used behind the scenes to program the shader units. And now the last thing we should know here is this technique. Think of techniques as, so there's this pass, and it's going to call each of these things, so the vertex and the pixel shader, single pass that's run. Now you could ultimately have multiple passes through a shader, so you'll see later on we do a for each through the effects. This is why. But basically, this is the script behind that basic effect. It's built in, you don't need to do any of this, you'll never have to touch this if you don't want to do your own shader stuff, but I thought you should be aware that it exists. And again, you can actually download the code for basic effect. There's also a CS file for basic effect right there. So this is a pre-compiled code that we're ultimately using when we create a basic effect. So, wanted you to be aware of it, but you don't necessarily have to do anything with it. But that is behind the scenes. When we are creating this basic effect, we're creating and binding to this shader. But that shader is going to depend on a couple of values. And we've already created them all, so it's not a lot more work, but we're going to have to pass in the view, the projection, and the world matrices for it to be able to do its magic. So that's why we went ahead and created all of those things. So now let's go ahead and create our basic effect. Basic effect. Coincidentally, if you want to apply your own shader, you can. You can replace all this. There's a link actually on Gamefromscratch again for how to go about that process. So, basic effect, and all you do is pass in the graphic device. If this seems like a lot of work, don't worry, because generally what you do is you write this kind of code once and never again. There's some values you can set on basic effect, for example, alpha. So we want full opaqueness, like so. Now the last thing that we want to do here, since we're passing in triangle data, but not textured or anything else like that, so we want basic effect dot vertex color enabled. So there, that way we can see our colored vertices. And we're going to create 3 different colors, so you're going to see this pretty effect, basically gradient color effect. And next up, since we don't have texture mapping, we don't have all of our lighting, we don't have normal information, we can't turn lighting on. And by default this won't be on, but I'm just being thorough here. Dot lighting, because there's actually a simple primitive lighting system built into the basic shader, but we're not using it. We'll use it later on, don't worry. But in this case, we'll turn it off because, as I said earlier, our shape is not actually going to have any normal information, and that is required for proper lighting. And finally, let's create our triangle. So remember earlier we declared an array of vertex position color. Let's allocate it now. Triangle vertices equals new. Hey, you failed me. Vertex position color array. 3 points in a triangle, obviously. That would be the try part. And we'll just create each one by hand. So 0 equals new vertex position color. And each one is going to have a vector 3. And it will be at 0, 20, and 0. Now, remember I said earlier with the camera, we set it up for like 0 is close, 1000 is far. I said these numbers mean nothing, just be consistent. Well, that's what we're doing here. We're setting our coordinates. We're saying that this vertices is at 0x, 20y, 0z. They're all going to be at z, so we're at the same depth. But that's essentially what we're doing. Then finally, we need to pass in our color information. And we'll make this vertex red. I think I got the right number here. Through the power of cut and paste, I'm no doubt going to make an error now. But let's create each of our other vertex. So this one, we want it to be at, okay, so 20, and minus 20, and again 0. And this one will be at, oh wait, no, we're going to do that one at minus 20. So left 20, up, or, so draw relative to the origin. The first one is straight up 20 and not left or right at all. The next one is down 20 and left 20. And the last one's going to be down 20 and right 20. Basically creating a 40 pixel per side triangle about our origin. So let me actually do what I just finished saying. And like I said, we're going to create that gradient. So let's set a different color for each vertex. There's no particular reason for this. It just creates a slightly prettier result. Okay, so that is a triangle basically defined in 3-dimensional space. Now let's create our vertex buffer. A vertex buffer is what is actually sent to the graphics card that contains our graphic information, basically our triangle. It's going to be copied into a vertex buffer. So new vertex buffer, and pass in the graphics device. Oops, I said device. All right, let's try that again. Graphics device, comma. What else do we need? Type of, so we're going to tell it what's in our buffer, and it's a vertex position colors. So, like so. There are 3 of them, and it's a write buffer. Buffer usage dot write only. Okay, done. So we just basically think about this as an array of drawables that we just dumped out to the, we're going to be dumping out to the video card. And that's it for our setup. So quick recap, position in space, target of the camera, position of the camera, create the lens, position the camera, and position the camera in the world, which is basically nothing. So there's no global transformations happening here, so the world matrix is basically empty. Now, what do we need to do? Oh, we need to actually have our camera do stuff. And we're just going to respond to keyboard events. Obviously, you could use the gamepad, etc. So if keyboard.getState.is key down, keys.right. So if you press the right arrow, do this. And we don't want to do that for left. This is fairly mindless code. And all we're really doing is updating our camera position accordingly. So in a left case, camera position.x minus equals 1. And we're actually going to do something here. So we've got to set up our camera looks at 0 and our camera's position is offset 100. But if we move the camera only, we're going to basically start an orbit effect. And I actually want to move both. So I'm going to pan both the camera and the camera's target at the same time. Otherwise, you sort of, by moving the camera but not moving the target, you'd create a rotation instead. And that's not what I'm aiming to do here. So cam target.x minus equals 1f as well. Like so. And we're going to, oops. Just flip the sign. So, right arrow, left arrow, and up and down. And in this case, we're in Y land. Remember, Y is up in the world of X and A. So up would be a minus, down will be a plus, I think, but I always screw that up. And now let's implement zoom. You know what, we can use the same logic. So it's called OEM plus. I'm going to use the plus key to zoom in and the minus key to zoom out. And in this case, we are altering Z. And I think for plus, I want to increment. So we're going to zoom out on plus, unless that doesn't make any sense, but oh well. And then here we'll do a minus. And then, so that's zoom in, zoom out your camera. And finally, we're going to use the spacebar to toggle orbiting, sorry. So if keyboard.getState is key down, keys.space. All we're doing is, if orbit's true, make it false, otherwise true. Oops. Let me just actually make my logic work. So we just flip the value of orbit. And then we'll check if orbiting is actually on. In that case, let's create a rotation matrix around the y-axis. And again, this is a tricky thing to do if you are not using the built-in libraries, but we are. So create rotation y. So we're creating a rotation matrix around the y-axis, again in radians though. So math helper 2 radians 1 degree, like so. And now that we've done our rotation, all we do is apply that to our camera's position. Equals vector3.transform. So what we're doing here is transforming our cam position by our rotation matrix, like so. And done. And now that we've modified all of those things, we need to create our view matrix again. Create, look at, same logic as before. It's just we now have an updated cam position, potentially a new cam target, and well, the same up as before. All right, So that's all we do. We basically use the arrow keys to pan left and right, up and down, spacebar to do the rotation, plus and minus to do zooming. All those things affected either camera position or camera target, which we then create a new updated view matrix. So you can see you basically just update your camera by updating your view matrix. And done. Finally, now we come to the rendering portion of this program. The logic is going to look a whole lot like it did. First off, we're going to go with white instead. I'm kind of getting sick of cornflower blue. It looks a bit like we did when we worked with, come on, Bram. Oh, Sprite Batch. But instead we used the basic effect. And as I said earlier, with the basic effect, you need to send in the projection view and world matrix, but it's a simple process because we've already created them all. View world. Now you could probably optimize this a bit by only actually updating the view because nothing else is being changed from the beginning. So you could have done that allocation somewhere else, but we're talking a minuscule amount of processing power. Now, as I said earlier, we created our Vertex Buffer, and that's what's going to be patched to the video card to be rendered. It's time to do that. So that's by calling graphicsDevice.set Vertex Buffer, and we pass in our Vertex Buffer like so. And now this part is fully optional. We're doing something called turning off backface culling. Now, backface culling is it's an optimization trick of basically well, not really a trick, but it's an optimization setting saying, all right, this has a direction and a normal, and it's a one-sided shape. So when you draw a triangle, it's only really visible from one side. So what the backface culling will do is turn off the backs of all the rendered polygons, things that aren't seen. Well, in this case, we're going to be orbiting around, so we don't actually want that behavior. We want to draw our vertexes from both sides, or sorry, our triangle from both sides. So what we're going to have to do is turn off the culling, or backface culling as it's generally called. In this case, all we do is create something called a rasterizer state object. Rasterizer state. New rasterizer state, like so, and then rasterizer state cull mode equals cull mode dot none. So now when we rotate around our shape, it shall work beautifully. Again, totally optional. Most of the time you probably won't need to do that setting, but for this example to work with orbiting, I needed to set it. So now finally that we've actually created that settings, we need to apply it. And this is raster state equals rasterizer state like that. And then finally, we loop through all of the available passes, of which generally there's only one, but there could be multiple. And so for each effect pass, now as I saw earlier, we know that the basic effect actually only has one technique in it, but we'll do this the right way anyways. Pass in, so basic effect dot current technique dot passes like that, and apply the pass, and graphics device dot draw primitives. Now this is basically saying to draw that buffer we've done, and you're going to now tell it what that buffer is composed of. In this case, it's composed of a triangle list, of a single triangle. So you pass in primitive type, and you see there's line strip, line list, triangle strip. Triangle strip is like a specially formed triangle data structure that keeps in mind that if you've got, say, two triangles that share a common side, you can kind of have less information as a result because it's a strip, so you're reusing two of the vertices for the next part of the strip, etc. But in this case, we're just doing a list. 0, 3, close. And our base draw is done. Okay, so basically loop through all of the effects in the shader, apply them, and then draw our primitives. And that is it. That's a lot of code. I'm going to have probably screwed this up. We shall now find out. So, wish me luck here. Play. that was funny. I was wondering why it was loading audio effects. That was the last example. All right, set a startup project, and let's try this again. All right, did I just curse things by switching this away? Let me see if that's showing me what I made as a mistake. All right, I did make a mistake. Give me a second here. I'll figure out where I did. Oh, okay, that was epic stupid. First off, I missed a minus sign here, but that really wasn't it. We would have at least probably gotten a line. Certainly a mistake, but not as big of a mistake as I actually did. I created a Vertex Buffer. I didn't put anything in said Vertex Buffer. Let's try that again. So Vertex Buffer dot set data. Yeah, sorry about that. Vertex position color, like so, and pass in our try. Why am I not getting my trying? Oh my god. Okay, I gotta change that too. I can't call them triangles. Give me 1 second. I gotta refactor that. Rename. Triangle vertices. Let's do that. Okay, much better. So this is the biggie I forgot. So you actually, after you create your vertex buffer, you actually have to put data in it, which is what this set data call is. You tell it the type of data you're setting, and of course the data you're setting. And now when we run this, hopefully, there we go. We have our triangle. Ta-da! That's about it. Yeah, I think that is a full-blown example. Now what we're going to do very quickly, because I'm already at the 40-minute mark, I'm going to show you how to use a 3D model. Now, what we just did there might seem like an awful lot of code for just drawing a bloody triangle on screen. And the reality is, as I said earlier, this is generally the kind of code that you throw off into a library somewhere, write it once, and never deal with it again. So don't be overly afraid of that aspect of it. However, what you're about to see now is when you're dealing with a 3D model, it's actually quite a bit simpler. The basic effect is built into the model itself. You obviously don't have to, so you don't create a basic effect anymore. You still need your world view matrices, etc. You don't need to create the triangle by hand. You don't need to set the vertex buffers. You don't need to set up your basic paths, etc. So it's a lot simpler to work with a completely created 3D model. So let's go ahead and create one now. So first off, I need to go ahead and let's create a new project in 8, I think. And this is example 2. Okay. All right, perfect. So now, power of copy and paste. First things first, I always forget this part. Switch that over. Set that as our active project and run. Perfect. All right, so we have working code. Now we're going to hack and slash and make it work with the model. When I say a model, I actually have a video on how I created this, but this is the guy we're going to use. This is a 3D textured model. There's the texture. Here's what it looks like in Blender. Ignore that. That's just because there's no light there. So if I went ahead and let's see, mesh. No. Oh, I'm in edit mode. Let's go back to object mode. Add lamp point. See? So that was just a side effect of Blender. So there is a full texture on every side, as you can see. And this is the model we used. We exported it out to collada format. You really wish to quit? Yes, I really do. So I created this file here, a DAE extension file, and there is our texture. Now to add this guy to our world, we go back to our trusty content pipeline, like so, and add existing items. And first we shall add that texture right here, like so. And next we shall add that model. This is just like using the content pipeline for any other thing like we did in the past. It's just, in this case, here you go. It's using something called ASIMP. It's Open Asset Import Library to do the importing. There's a bunch of settings you can do. So even, remember sort of earlier I said the up axis can change things, and if you needed to move them or change them or rotate them, you can. You can actually do that as part of your importing value as well if you wished. I don't care. I'm just going to let it be 90 degrees off kilter. But you can actually change that as part of the input process if you desire. So now let's go ahead and save and build. And success. So we now imported our model and our texture into our world. Let's look at the code for loading a model instead. And that is going to take a lot of hack and slash. So like I said earlier, no longer need. Yeah, we'll still orbit. That works for me. Oh, I didn't actually show you any of the controls. Oh, here. Sorry. Let me go back. Set a startup and run. So this is the previous project we were just working on. If you use the arrow keys, you pan around the scene, up and down, plus and minus. All right, apparently I have minus and plus mapped to the same thing. Oops. And let me just go ahead and start that again. And then spacebar starts orbiting. And here, it looks like the triangle is rotating, but it's not actually. This is the camera rotating around the origin. That's when we did that create create rotation Y effect. Basically, this is our camera rotating around our triangle. And if we hadn't set that color mode to none, when we got behind the triangle, we would actually see nothing. So that's why we set that. So anyways, that's the end result. And then spacebar again to turn off the, spacebar again turns off the orbiting. And on, and off, and on. And let's close that down. So that was the end result of that example. Now, I said I seem to have done... Yeah, I did a plus here. So this should be a minus. My bad. So otherwise, you're good. And yeah, I got no idea which one I have open now. Example 2. Okay, so that we're back now to our new project. Let me set it back as active. Sorry, I forgot to illustrate that camera we spent so much time working on. My bad. So we no longer need the triangle. No longer need the vertex buffer. All gone. And everything else stays the same. We're still going to manipulate the camera as normal, but no more basic effect, no more setting of the vertex buffer, actually no more backface culling, and no more effect pass loop. So greatly simplified code. What we do now, however, have to do is load our model. So it's in our content as, what did I call it? MonoCube. And now we need to load MonoCube into our game. All right, and this is a whole lot like before. It's like working with a sprite, just with a 3D model instead, and that is called, predictably enough, a model. And then initialize here, or actually, let's be right and do it in load content. I don't think I did in my example on Gamefromscratch, but I should have. So anyways, model equals content.load type model, like so, and it was called monobuse, monocube, like so. So that's it. That's all that's involved in loading your model. We're not positioning it or anything. We'll go with the default, which I believe is going to be at the origin anyways, which is good. So now we just have to update our draw code. So we're still going to clear it at blue, but now we are going to, remember I said earlier, the model actually has their own effect built in. Very cool. Now the other thing is a model can be composed of multiple meshes. In this case we have a single mesh, but it could actually be dozens of meshes in there, potentially. It could actually be an entire level. So what we need to do is first loop through all of the meshes in a model. So model mesh. Now a mesh is the geometric data, the triangles or polygons that make up the model itself, as well as the UV information, etc. that goes with them. So that's our mesh in model.meshes. Like ta-da. And now for each of those, there is a basic effect built in. So basic effect in mesh.effects. Effect.ambient, oops. I don't know why I do this. I don't think it actually does anything, so I'm not going to bother doing that. I'm going to set an ambient light. I don't know why I did that in my text example. I probably shouldn't have. So all we're going to do is set up the view. I Bet you can guess the next two. World and projection. So the effect script for each of these also needs those three pieces of information for basically positioning things in the world. And this would be generally if your cube was somewhere located elsewise, you would have modified it here. So if it wasn't just about the origin like we're doing here, that's where you would actually set the position of your model. So mesh.draw, or I suppose you could do it in the positioning of the overall model itself. So that's it. So here's your draw call. Basically, it goes through all of the meshes in your model.meshes collection, and then for each one, it goes through all of their effects, which the fact that it's a basic effect is going to probably be a loop of one iteration. Sets the view information required by that script, and then we draw. Actually, this doesn't make any sense. Should actually technically be drawing inside. So, all right. Ta-da. Now, let's go ahead and we're set up. In theory, yeah, let's go ahead and run. There you go. Now, probably not what you were expecting to see, but there's a very good reason behind this. Remember when I said earlier on that the numbers we use don't matter? And they don't matter. They really, really don't. So when we created our triangle, which was 20 up, 20 left, 20 right, so a total of 40 by 40, we set our units relative to that amount. In this case, though, we're bringing it in from Blender, and I believe this by default is 2 by 2. So our shape, as opposed to being 40 by 40, is 2 by 2. And as a result, our camera is quite far away. That's easily fixed here. Where do we set the camera value? So instead of being back by, say, 10, by 100, let's be back by, say, 10 instead. So go ahead and press play, and there's the result. It's probably, again, orientated wrong because of the different up axes compared between the 3D programs. Again, you could switch that in your 3D program on export. You could do that on the content pipeline on import, or you could do it in code to fix that orientation. So it's not something I'm particularly concerned about. It's also one of those things you could actually do in your world matrix transformation if you really want to just transform everything by 90 degrees. Not really a performance hit involved in doing that either. So left and right, and there you go. Plus and minus, zoom in and out. Now, since we're setting in the orbit camera, you'll see if I zoom through it, we actually flip through to the other side. And then minus becomes plus, which makes sense, because we're looking at the axis and then zooming around it, essentially. But what you'll notice is, and I'll zoom in a little bit, so notice how this back edge, right, oh, there's no mouse cursor turned on. Okay. And I would show you with my finger, but that's not very effective. But the front edge of this texture, in between, say, H1 and A8, that edge there is a lot bigger than that back one. And that's the result of being the perspective camera. Had we created an orthographic camera, that front and back edge would be the exact same size. And it gets more pronounced as you move off. See? That's the effect of your perspective camera. And it does give you a better illusion of depth, but if you're creating a game that's involved sprites, you obviously wouldn't choose that. So anyways, that is introductory 3D in MonoGame / XNA. It's scarier than it looks, and again, generally this is the type of code you write once and you're done with. And as you saw here, when you're working with models, it's actually a lot easier than actually creating these primitives yourself. You could also create your own model class, which is loading. A model is ultimately a collection of vertexes, normal information, and textures. So you could do it with drawing textured primitives and create your own class if you really wanted to. I'm not sure if the code is available or not. Not a big deal in the end. That is essentially 3D. I hope that all made sense. We might cover things a little bit further on in the future, but that should give you a pretty solid foundation. The biggest thing is really getting your head behind those three matrices, how they go together, basically position your viewpoint within the scene, and that relationship between the basic effect and those matrices, and how that's used to actually draw things to the screen. But that's it. Thank you very much. Have a good day. Bye.